Welcome back to another riveting episode of Dave Does Math from Home. Today we're talking about section 2.5, which is very much like section 2.4. I'm hoping you're watching these kind of back to back because they have a lot to do with each other. Section 2.4 is where we plugged numbers into functions and we got infinity out. Sort of the infinity was the unofficial output of the function, and it can't be the real because that's not allowed, but we can pretend like it's real by using the word limit. 2.5 is going to be very similar except sort of backwards. Instead of plugging a number into a function and getting infinity-ish out as an output, now we're going to be plugging infinity into the function and seeing if we get numbers out instead. So that's going to look like this. The limit as x approaches infinity of f of x, or the limit as x approaches negative infinity of f of x. These are the two topics we're going to deal with in section 2.5, limits at infinity. We're going to see what happens when we plug infinity or negative infinity into this function. And here's the very interesting news about this. Secretly, I've been tricking you into doing this for months. Think about what this means. Limit means what the function looks like. And x approaches infinity means x is big. So the limit as x approaches infinity means what the function looks like when x is big, which hopefully is extremely familiar to you all, because these are the exact words that I used to describe end behavior all throughout pre-calculus. Every time we talked about end behavior, we were talking about end behavior for polynomials, we were talking about end behavior for rational functions. We never explicitly used the words end behavior for exponential functions, but we did talk about the horizontal asymptotes that they had, and horizontal asymptote is a form of end behavior. So we were secretly talking about this the whole time. And the whole time we were talking about this, we were secretly talking about limits. End behavior is the sort of pedestrian version of limit as x approaches infinity. But they're secretly, I guess not so secretly if I'm about to post this publicly on YouTube, they're secretly the exact same concept. So section 2.5 is just entirely about end behavior. The interesting distinction is that we're going to split it up into two parts. Like when we did end behavior for polynomials, we were kind of lumping both the left end behavior and the right end behavior into the same category, which is how we ended up with end behaviors like the field goal or the disco left or disco right, because we were looking at both of them at once. In this section, we're only going to look at them one at a time. So we're either going to take a limit as x approaches infinity, and we'll see if that's going up or down or turning into a number. And then we're going to take a look as x approaches negative infinity on the back end and see whether that's going up or down or giving you a number. I'm probably gesturing in the wrong direction. I cannot keep track of which way I'm facing, and my seeing myself in the camera mirror thing is kind of screwing with me a little bit. Anyway, we'll do it. Infinity is what happens over here. Negative infinity is what happens over here. We'll treat with them separately. So let's first take a look at what these look like for polynomials. If we take something like f of x equals 7x to the fourth minus 23,000 x cubed plus 15x, and I want to know what is the limit as x approaches infinity of f of x. To answer this question, I need to look at the end behavior. The end behavior of this polynomial, we remember from pre-calculus that since this is even and this is positive, This being even means they're both going to go in the same direction, either both up or both down. And since this is positive, we know they're both going up. So this end behavior is field goal, which means that the limit as x approaches infinity is infinity to the right. The limit as x approaches negative infinity is also infinity to the left, because it's going up in both directions, because that's the field goal. If you have something like disco right means that when x goes to infinity, the function goes to infinity, and when x goes to negative infinity, the function goes to negative infinity. Disco left is backwards, and hammer time, if you were familiar with that version of the they both go down end behavior, would have them both being negative infinity. That's the entirety of end behavior for polynomials. You start plugging infinity into these guys, really, really, really big numbers into these guys, you're going to get infinities out. Next up, let's take a look at exponential functions. So we'll say f of x equals negative 3 to the x plus 2. So again, if we remember our transformations, this is going to be shifted up 2, and this is going to be flipped upside down. So, in a very quick sketch, come on marker, hold together. In a very quick sketch, I'm going to have a horizontal asymptote at 2, and I'm going to be going upside down from there. So, if I want to talk about the limit as x approaches infinity of f of x, the end behavior in the positive direction is going to be negative infinity, and the limit as x approaches negative infinity of f of x should be 2. That's where that horizontal asymptote kicks in on the back end out there. We're going to get 2 the further we go this way. It's going to look more and more and more like the number 2. So, for exponential functions, you have to figure out which side of the graph is going to be asymptotic. For most graphs, it's going to be on the left. Usually, exponential functions follow the asymptote on the left of the graph. If your base is a fraction, or if your exponent is negative, like if you have a negative sign in here, those two things will flip the graph from left to right and give you a asymptote on the right side and whatever kind of behavior, the swoopy behavior on the right. So you figure out which side is your asymptote, and then that limit just is the asymptote, y equals 2. And on the other side, you have to figure out whether it's going up or down. It depends on whether your function's upside down. But this is all math that we've done before. We're just giving some fancy new terminology, fancy new symbols for it. Shouldn't be super surprising. And the very last thing we need to talk about is our favorite, rational functions. So if we have something like f of x equals 4x squared minus 16 over x squared minus 10x plus 21. This is a rational function. If I want to know about the limit as x approaches infinity, or the limit as x approaches negative infinity, I need to talk about the end behavior again. So we're back into the realm of things that we have extensively talked about the end behavior for in pre-calculus. So let's consider the end behavior here. The end behavior of this guy, when x is really, really big, just looks like these leading terms. So 4x squared over x squared, which simplifies into 4, which means that both of these should be 4. And you're done. That's all you got to deal with. If you get different rational functions, like maybe you get something like x minus 12 over x cubed plus 15x minus 80. If you get something like this, then you want to look at the end behavior, and you should see that it would be x over x cubed, which is 1 over x squared. If you get something like 1 over x squared, and you want to know what happens when x goes to infinity, you have to imagine sharing a single cookie between several trillion people. You're wondering how much of your single cookie each person gets. It's about 0. When you have 1 over x squared or x cubed, or even just 1 over x, as x goes to infinity, that's going to turn into 0. If you have, on the back end, at negative infinity, you're still getting 0. So if your end behavior looks like 1 over anything, that always looks like 0 when x is really, really, really big, or really big and negative. The third possible outcome you could get from this end behavior is if the numerator has a higher degree than the denominator. And that might be x to the 4th, we'll say 3x to the 4th, negative 3x to the 4th, plus 72x over x cubed minus 72x. So, if you have a rational function that looks like this, you can still look at the end behavior. That's just looking at the leading terms. We'll get 3x to the 4th over x cubed. This simplifies into negative 3x. So now if you're looking at this as your end behavior and wondering what happens when x goes to infinity, when x goes to infinity, negative 3x is going to be negative infinity. And when x goes to negative infinity, negative 3x is going to be positive infinity. And that's it. That's your end behavior. All of these limits always just come from the end behavior of the function. They should be really straightforward because you've been doing end behavior for months now. You just didn't know it was called limits. That's it for this video. Be in touch if you have any questions, and I hope that made sense.